Today's example for an AMOS application will focus on the topic of consistency, availability, and partitioning of data in a distributed system that exhibits failover and recovery across multiple databases. Modern distributed systems must continue operating even when individual components fail. However, they must also manage trade-offs between maintaining consistent data, remaining available to users, and tolerating network partitions. This fundamental tension is described by the CAP theorem. In this demonstration, we present an AMOS-based architecture that explores these trade-offs using a distributed database environment with multiple storage backends, dynamic service discovery, automated failover, and runtime system control. The goal of this system is to both control and observe distributed behavior under failure conditions. The architecture is organized into two major layers: a control plane, which manages system behavior, and a workload and measurement plane, which generates and evaluates system activity. This separation allows us to manipulate system conditions while independently observing their effects on data consistency and availability. The control plane provides centralized management of the distributed environment. The manager front-end provides a user interface for controlling the system. From this interface, we can start or stop database services, change routing policies, observe system topology, and inject failures. This enables controlled experimentation with system behavior. The database manager acts as the central control service. It receives commands from the front end and coordinates operations across the system. Its responsibilities include discovering available services, maintaining a registry of database proxies, monitoring health status, and routing control commands. The database manager ensures the system can dynamically adapt to changing network conditions. The Manager Application Event Manager, or AEM, provides orchestration and routing. It determines how operations are distributed across databases using configurable strategies such as broadcast execution, round-robin load balancing, or primary-secondary failover. This allows us to explore different consistency and availability behaviors by simply changing system policy. Finally, database proxy services provide a uniform interface to heterogeneous storage systems, such as MySQL and PostgreSQL. These proxies expose health and lifecycle controls, manage database connections, and enable runtime failover. Because all communication passes through proxies, the system can transparently redirect operations when failures occur. While the control plane manages the system, the workload plane measures how it behaves. This layer simulates real application activity and tracks outcomes. The transaction service generates database workloads at a controlled rate, measured in transactions per second. It continuously writes and reads data across the distributed system while reporting system throughput, database availability, and data visibility across storage backends. This provides real-time insight into system performance. A separate event manager handles transaction execution. It distributes read and write operations across database proxies and aggregates results. It also produces a merged view showing which databases successfully processed each transaction. This allows us to directly observe consistency across storage systems. In AMOS, the APM reads an application manifest as a YAML file that declares the deployment environment and each containerized service. The manifest includes the cluster target, the graph name used for topology tracking, and a services list where each entry defines a container image, port, runtime resources, and environment variables. At deployment time, the APM uses each service entry to create a runnable unit with the specified image, CPU and memory, exposed port, desired count, and injected environment variables. Because the manifest enables an assigned public IP, the APM can return a routable endpoint for each container as part of its deployment output. While the deployment YAML defines how to deploy containers, the schema defines how those containers relate in the AMOS graph model. Vertices represent services and edges represent intended communication relationships. This matters because after APM deploys the services and learns their real addresses, the SEM can produce a topology payload for who communicates with whom and posts it into each service's network config endpoint. That's how services become self-wiring. AEM learns which proxy URLs exist based on edges. The control plane AEM similarly learns MySQL/Postgres proxies based on schema edge substrings and expected ports. Using this architecture, we can simulate failures such as shutting down a database, interrupting connectivity, or restarting services. The control plane detects failures through health monitoring and reroutes operations to available components. Meanwhile, the workload plane reveals whether transactions remain available, how data consistency changes, and how quickly the system recovers. This demonstrates real-world distributed system behavior under fault conditions. This system illustrates several core AMOS design principles: autonomous components capable of self-management, dynamic network configuration through runtime topology updates, separation of control and execution layers, and continuous monitoring and adaptation. Together, these enable resilient distributed computation. This platform provides a controlled environment for studying distributed systems behavior, including KP trade-offs, consistency models, replication strategies, and failure recovery mechanisms. It enables reproducible experimentation by allowing system state to be manipulated while measuring observable outcomes. Here we can see transactions actively flowing through the system. Each transaction is being written through the manager layer and replicated into both MySQL and Postgres. As traffic continues, both databases increase their transaction counts in real time. Now I'm going to stop the Postgres database to simulate a failure. As expected, Postgres stops accepting new transactions. However, MySQL continues running and continues receiving writes. This demonstrates that the system can tolerate a database outage while continuing to process transactions. At this point, we can see that the transaction counts have diverged. MySQL has continued to grow, while Postgres remains unavailable. Now I'll restart the Postgres database. Once it comes back online, the manager automatically performs a synchronization process. The system checks the highest transaction ID present in Postgres and compares it to the MySQL database. It then requests all missing rows, starting from the last known transaction, and applies them to Postgres. After synchronization completes, both databases return to the same transaction count. Postgres has successfully caught up to MySQL without losing any data. This demonstrates controlled database failover and recovery with deterministic replication. Even if one database goes offline temporarily, the system can restore consistency automatically once it returns. The application continues operating, and the data layer heals itself. In summary, this AMOS application demonstrates how distributed systems can balance consistency and availability through dynamic orchestration and monitoring. By separating system control from workload generation, we gain a powerful framework for exploring fault tolerance, data consistency, and recovery in heterogeneous database environments. This approach provides a foundation for building resilient distributed applications and studying their behavior under real-world conditions. Thank you, and we look forward to sharing our next example of an AMOS application.